Thanks for coming to the talk. I've spoken on this sort of a similar topic like 3 years ago in this seminar. And today I want to give you like a review and update on this project. So I guess the history of the project is like Mina came up with 2 ways to realize categorify not invariant. One using the B side coherent sheaf of some Coulomb branch, and one is using the A side. It's a Fukaya category of multiplicative Coulomb branch, some space, and then we. For me, as a sort of a symplectic geometer, we try to work more on the A side, and we studied what is the Lagrangian branes in this space and how the endomorphism algebra look like for those Lagrangian branes, and what is the categorification of the raising lowering operator. And we also discovered something new. For example, how do we glue surfaces together, and how to use that to realize the categorified tensor product of representation of quantum group. So I'm going to talk today and next week. So the plan for this talk 1, is just to explain what is our theory. I.e., what is the space we're doing categories on, what is the Lagrangians, and what are the morphisms. And these consist of saying what's the category associated to some input data, like what is the highest weight and the weight for a given representation. And then we'll also talk about how to do functors between such categories, where we will see how braiding arises and how how cap and cap, and maybe more generalized cap how the web, and how merge and cut of surfaces arises as functors. So that was maybe sort of an ambitious plan for the talk 1. Talk 2, next time I'll explain what kind of the structure exists as underlying our theory. So our theory is like one example for those structures. So we call those structure, you can call the structure Hopf category, or Hopfish category, or HF category. I haven't decided on the name yet. It's also related to a categorification of something Kapranov and Schechtman proposed, which is a factorizable perverse sheaf. So here we have factorizable perverse Schober. So this is, we're going to propose a set of geometric axioms. This is related but different from a similar axiom proposed by Hopf and Wedrich, which also categorifies Kapranov-Schechtman's proposal. So that was a plan for the next talk. And for today, we don't worry about all these axioms, just to say what is our theory is. Okay, so the Fukaya category. Associated to the following data. A UQG, we fix a ADE, the algebra, and we fix a lambda, which is the highest weight. So it's a dominant. We also fix a mu that is subdominant to lambda. So mu is lambda plus lambda minus certain positive roots. Say, let's call that K1, KIEI. I from 1 to R is the rank. And EI are the simple roots. For most of the time of the talk, I'm just going to focus on type A, and actually just the SL2, just for concreteness. But this whole formalism applies to general ADV algebra. So for example, G is SL2. The Dinkin quiver is just a single node. SLN is just n minus 1 nodes. Okay. So I'm going to use a quiver notation to remember what is a lambda and alpha. By alpha, I'll call this alpha. So for now, fix G to be SL2. So the quiver I'm going to consider is a framed quiver. Put N here and K here. As my lambda is N times W1. W1 is the fundamental of SL2. And alpha is K times E1. For example, C2 has highest weight, has lambda is equals to W1, the first fundamental. And the C2 has two weight spaces, which is the W1 and the W1 minus alpha. Sometimes we identify this with 1, and this is a negative 1. Okay, so given this data, I'm going to tell you a space that's going to be the playground for the Fukaya category, a symplectic manifold. I'll denote that with YK. YK has several ways of description. One way is the so-called additive Coulomb branch. Which is given by some 30 equal to 4 gauge theory, where G gauge is GLK, and the representation GXN representation is a representation given from this quiver is from CK to CN. So this is defined by Braverman, Finkelberg, and Nakajima. One can write down very concrete coordinates on this, but that's pretty hard to define. There's another way to think about the space. Before we go on, let's reassure you that such space is going to be smooth affine. So here I probably should put some subscript. This is affine deformation. That depends on certain parameters, A1 through AN, distinct parameters in C. All right. Okay. So in some nice cases, sorry, not in some nice, always in this case, you can also realize this as a generalized Grassmannian slices in GLG. Here, this G is not that G gauge. This G is the group corresponding to the thinking quiver. So G is SL2. Still, I need to tell you what is this generalized Grassmannian slices. This is defined in also by BF in the second paper with the title Slices to Grassmannian. It's called BFN2. But I can tell you for some very simple case, for a special case where n equals to 0, which is captures a lot of those interesting thing. This is going to be the open, so-called open Zastava, and it has a scary name, but it's a very concrete definition. It's about the holomorphic maps from a domain P1 with special point infinity sent to a target P1 with a base point 0 of degree k. Okay, so very concretely, what does this mean? It means that you have a degree k rational function written as qy over py, where py is monic of degree k and with coefficients ai. And qy is degree less than k. Okay, such that you want there's no common factors between the two polynomials. So GCD of q and p equal to 1. Okay, so this space, let's call that YK. Is just an affine space given by all the AIs and BIs and removing a divisor, which is called the resultant of P and Q equal to 0. So this is a polynomial in the coefficients AI and BI. So as you can see, this is a clearly smooth affine, this space. So this YK space, how to think about that? It admits a map to sim KC, which, if you wish, is the same of just CK parameterized by the AI variable. Sim KC is parameterizing the zeros, the roots of P. So you can either say they're just by unordered K points on C, or you can remember their coefficients of the polynomials. Given this map pi k, a generic fiber of pi k is easy to describe. Pi k. Say py is given by y minus y1, y minus yk. Then if you fix y1 and y through yk, you fix the polynomial, then qy over py, the freedom, the fiber is parameterized by admissible q. So this can always be written as the following. Where ui is not equal to 0. Okay, so the generic fiber is so pi k inverse with the unordered n tuple can be parameterized by c star to the k, u1 through uk. Okay, and what happens when like two of these y's collide? Then if something non-generic y1 equal to y2, but not equal to y3 and so on, then you can write your qy over py as y minus y1 squared. And then you can say, here we have y minus y1 plus beta. And then you keep on going y minus y3, u3, and so on. So we also, the u1, u2 freedom becomes the coefficient, local coefficient of the numerator, alpha and the beta. The condition for alpha and beta is just beta is not equal to 0. The reason we want beta to be not equal to 0 is that when beta equals to 0, then you do not have like a k poles of the function, you have k minus 1 poles. That means there's some common factor between q and y, which we forbid. There's no common factor. So beta is non-zero. So fiber is c times c star times the other ui's. So this is just giving you an example to show that using this this open Zastava picture, it's very easy to describe what the fiber is. All right. So I described for you this additive Coulomb branch with a box n being non-zero, and this additive Coulomb branch with no boxes. But actually, our space for whatever n and k will always be this space, this yk. And you may wonder, where does the choice of n, where does the highest weight dependence gonna go? It will come into a different piece of information, the superpotential of the space. Let me write down the superpotential. Still XA4. Suppose you have to have n equals 0, the superpotential W has two parts, WF and W, it's called WB, or more precisely, a function put back from the base. So WF is going to be, informally speaking, on the open loci, U1 plus UK. You sum up all the residues over each pole. However, this UI coordinate only good on the open loci, but this together extends into a nice function, which is just the leading coefficient of QY. We're never going to use this BK minus 1 function explicitly because our calculation will happen on the open loci. So the U1 plus UK are going to be the more useful coordinates to remember. And if you have a quiver with framing n, we need to choose some parameters, AIs. These parameters, I use the A for those coefficients. I need to change it. So maybe I call that C, C1, Cn, C distinct. Then my my WF is going to be is U multiplied by the coefficient y minus C1 to y minus Cn. All right. Sorry, yi. And my WB will be some I, again, in the open loci, yi squared. If you think about the sum of yi squared, this will be just this will exactly be the coefficient of, well, some linear combination of coefficient of these two guys. So, minus 1 squared, minus 2, okay, minus 2. Okay, so this is, again, this is the useful things to remember. Was that? No, this is like the form of W on the open part. This is like expressed using global coordinate. Those A's coordinate are like the global coordinate, AI, BI. Yeah, but these are like the useful form that we will use. I didn't say why it's useful yet. WB, yes, WB is some choices I make. In general, you could, this could change. Maybe this could change like Y1 or Y2, Y3. This is going to be, corresponds to the choice of a disk with 2 stops, which I'll explain what do I mean by those things. And these CI variables are going to be locations of certain punctures or not special points in C. Yeah. Yeah, sorry. Yeah, these are the C's. The space we're actually working on is this full Coulomb branch deleting some divisor. After deleting those divisors, it will become just this Coulomb branch, as if there's no framing nodes. And these function, this WF, this superpotential, were originally like regular functions on this bigger guy as well. All right, so we have this space YK, curly YK, and we're going to define this open loci YKO inside YK, where YKO are very generic. It is where this yi is not equal to yj, and this yi are not equal to either of the CL. The way to think about the setup is, as I mentioned, there are some fixed special point here, and the base sim kc sub y parameterize k moving points on the space. When the k moving points are all distinct and distinct from this kind of a point, then you have like this big open strata, and things are easy to analyze. Our Lagrangian will be living in this kind of a space, and the holomorphic disk are allowed to pass anywhere. So in a sense, it is like a relative Fukaya category where the Lagrangian are nice, but disk can do whatever they want. Okay. So how to talk about, so the category, if I just stop here, I can just tell you that the category is the Fukaya et al. Category of the space YK, and with the superpotential, W. Okay, that is the category we're looking at. You can associate a picture to that is with this two stop and a bunch of mark points in there. And we put a subscript K there to indicate there will be K Lagrangians, K tuples of single Lagrangians to make whose product will be a Lagrangian in YK. Okay, so let's talk about Lagrangians.
Probably need also, because Q, right, you'll need some more parts of it.
Right. I had swept under the rug a very important information to relate to the UQ. There's
crucial, right?
Yeah.
Without that information, you could say, well, so I don't want to think about that.
Exactly. Okay, let's also mention that. So this space YK, how to say? This space YK has a map. It's called a theta to C star. This theta map. Let me think for a second. Yeah, I need to. Right, so there is a map from yk to theta, and we can make the Fukaya category, make this Fukaya category is Hopf space, Hopf space Z graded. Z graded, or let's say maybe. So one of the Z grading comes from the usual cohomological grading. One of the Z grading comes from the Q grading, where the Hopf space between two Lagrangian, you can think of is given by some ripcord, and if you project those ripcord to C star, you can count certain winding number, and that winding number gives you the extra Q grading here. We'll see those Q grading come up later in the concrete examples here. Let's put it aside. All right, now let's talk about the Lagrangians here. So this high dimensional space is very hard to think about. How can we concretely cook up Lagrangians? We're going to use this map from YK from YKO to SimK C non-equal. This non-equal means yi not equal to yj. So for simplicity, let me first assume n equal to 0. So I don't need to worry about this condition. And at k equals to at k equal to 1, this is like the simplest, very simple case. So let's say what's the space looks like. So this is then yk equals to yko for k equal to 1 equal to 0. So the space is just going to be cy times, you can say, C star u. So I'm going to draw my space in the base, cy. I'm going to draw my space, C star u like this in the fiber. So the Lagrangian I'm going to consider are of the form a straight line in the base and a straight line in the fiber. So here, I also need to tell you what's the role of the superpotential in defining the Fukaya category. Here's this W equals to WF plus WB, which is U plus Y squared. The role of the superpotential in Fukaya category introduces something called a stop in the space. The stop basically is the, you can say, asymptotic directions in the space where the superpotential goes to plus infinity. Question, yeah. Sorry, CCL. Yeah, so not, yeah, not. Right, so you don't want any of the moving point yi to collide with any of this fixed point CL. Right? You don't allow any of this yi to collide with themselves either. Okay. So here, this is like u. So where this function can go to infinity is either where u can go to plus infinity, or y squared can go to plus infinity, which means y can go to plus or minus infinity. So I'm going to put some blob to say, okay, here are the stop. So Fukaya category with the stop, that means Lagrangians that stay away from the stop. So I'm going to draw my Lagrangian just to straight line, just avoid the stop. And you can see, like in this picture, this kind of a product of Lagrangian is like the unique Lagrangian you could draw. All right. So we call this Lagrangian T, or call them T brain. And this endomorphism of this T brain is going to be Z inverse, a Laurent polynomial. I won't have time to explain how to compute endomorphism in the Fukaya category. Sorry, all right. CZ, yeah. But I can just draw some picture to show you what calculations involved. To compute endomorphism of a Lagrangian T, you need to positively wrap the first copy of T. I'll keep the second copy like fixed. The first copy, what do I mean by positively wrap? There is some wrapping flow on the boundary for the manifold. The wrapping flows are normal speed here, but it gets stopped, slows to 0 here. So when you wrap, it never gets past that stop. Similarly, in the fiber, you wrap like this and go like this. Because here the bottom boundary has no stop, you can go on wrapping forever. That creates it's like positive integer many intersection point corresponding to the bases Z0, Z1, Z2. And the multiplication structure here is by counting triangles, which I don't show in this picture. Okay, so that's like the first example of this space and the Lagrangian in the space. Yeah. Oh, how do I compute the stop out of the superpotential? Yeah, the stop, roughly speaking, is where the superpotential goes to plus infinity. So here, my WF, I can compute the stop factor-wise. WF function on here, it goes to infinity along U is positively real. WB goes to infinity where Y is plus or minus infinity. No. As you can see, a line in C is not a holomorphic object. No. That's a very good question. When we talk about the holomorphic Lagrangian of this Coulomb branch, or this magnetic monopole space, there are different choices for complex structures. Maybe for one choice of the complex structure, these guys are indeed holomorphic Lagrangians. But here we're using a complex structure where these are just the ordinary Lagrangians. Yeah. Yeah, you see the wrapping on the both two boundaries are in the opposite direction. Yeah, the stop on the top stops it from infinite wrapping on the top. It has infinite wrapping in the bottom. Yeah, I should have drawn the blue guy getting stuck on the guy on the stop here, but I didn't. The what? Right, I will tell you what is the NT going to be. NT somehow is the key player that determines the Fukaya category. Because these T objects are going to be the generator of the category, and NT will be the, yeah. Yes, Yeah, you choose W. So this WF is the most, how to say, amazing or mysterious part of the theory. I don't have a good explanation. It's predicted by mirror symmetries, comes down from string theory. Yeah, and this WB is just by having the desire of having two stops here. If I only want to have one stop, I can just choose WB to be y to the first power. And the three stops is y to the 3 power. You have three directions for y to go, so that W goes positive real. All right. Okay, so this is one example of the Lagrangian. Let's do another case for k equal to 2. So I'm going to tell you a Lagrangian of the form LB in sim to C unequal. So this is going to be LB is LB1 times LB2. So LB, so this is LB1, LB2. So there are two Lagrangians in C that are disjoint. So when I take the product and the quotient by S2, they give me a Lagrangian in this space. Okay, so B2s in C2, removing diagonal. So quotient to sim to C. Okay. Yeah, two disjoint Lagrangians in C. Yeah, right, exactly. That's right, that's right. I want to draw a Lagrangian in a symmetric product, just to draw two distinct Lagrangians, disjoint Lagrangians. Of course, labeling 1, 2 doesn't matter. So these are like these things in the base, and if I want to specify a Lagrangian, total Lagrangian in the total space, Y20, I need to specify what lives over the fiber. So if I pick a point in LB, so call that P1, P2, then I'm just tell you what the fiber is. The fiber is going to be C star U1 times C star U2, U1 living over this guy, U2 living over that guy. And because I have chosen my superpotential to be U1 plus U2, again, I have stops here and here. So I'm going to choose the straight line Lagrangian in the fiber as well. All right, so just draw in our line. And this is, again, what I call a T-brane. And here, endomorphism of this Lagrangian is going to be interesting. So again, we're going to wrap both the base and fiber. Let's wrap the base first. All right. So apparently there are 4 intersection points, but the actual intersection point in this symmetric product are just going to be two points. One is this guy, one is this guy, the box and the triangle. The box intersection point, pair of intersection points, this represents identity because those intersection point appears after a slight perturbation of your Lagrangian. And these triangle Lagrangians, these triangle intersection points comes later. So the base intersection point has a bijection points. Has a bijection with the symmetric group S2. Because you can either swap and keep the same or swap them. So we label them by this kind of strand diagram. And the fiber over this kind of a pair of points or over this kind of pair of points, the fiber can have independent wrappings. So the intersections, total intersection points in total space is labeled by N1, N2, N1, N2. Where these Ni's are non-negative integers, telling you how many wrappings over each fiber this guy needs to do. For example, if over this intersection point, this will be Z0, Z1, and this is Z2. Okay, so these are like the intersection patterns. But what is about the algebra structure? So in the paper we posted last year, we computed the algebra structure of this guy, the morphism of this T-brane. Is equivalent to an algebra called the New-Hack 2 algebra. So this New-Hack 2 algebra has a diagrammatic presentation. So it's generated, it's about pictures in R cross this interval I of 2 strands. And the 2 strands, you can put arbitrary number of dots, arbitrary number of where. It satisfies the easy composition relation by just stacking the pictures on top of each other. And it satisfies 2 important relations. One is the Neal relation. Composition of 2 crossing equals to 0. One is sort of the Hack relation. Equals to H bar times identity. So we verified that in the Fukaya category, after some isomorphism, you can make the endomorphism algebra the same as the New-Hack 2 algebra. This H bar, right. For now, you can set that equal to 1, but this H bar represents the fact that the disk that contribute to this composition pass through the diagonal divisor once. Yeah, it comes from like the relative Fukaya category machinery, where you count disk weighted by how many times it passes through a certain divisor. We could set h bar equals to 1 just for simplicity. Okay. So that's like the basic setup for Lagrangian and the morphism. And let me also talk about how to deal with the case where there are punctures. When I say puncture, it doesn't mean I take away that point. It just means like there's something special about that point. It's a historical name. You can think of it as a marked point or defect. Yes. This new Hack-2 algebra, this comes to earlier work of Hovanov, Lauda, and Ruquier when they considered categorification of the algebra. That's where this new Hack algebra appears. New Hack algebras are the case where the algebra is SL2. For general the algebra G, they also have a similar cousin that's usually called the Quiver-Hack algebra or KRR algebra to honor these people. This is a special case for those algebra. Okay, great. So the Fukaya category is like, okay, smart enough to know about this algebra. What about the punctures? So let's also consider the simplest case where you just have one puncture and one strand. So the space is going to be, let's say, CY. I should call it X, but I haven't introduced the notation X. Let's call it U as well. So W1 is going to be Y minus C1. Sorry, let me just call this variable X because I want to reserve this name as my name for U. Okay. Okay. So one can think about the space is still just base is the C and fiber is the C star. And you have a base superpotential and a fiber superpotential, where this I denoted as the U variable. So if you fix a base point Y and look at the fiber, you have you can either use the U coordinate or use the X coordinate. If you use the U coordinate, then the stop's position is fixed. This location, this argument of this U, the stop is equal to 0. However, if you use the X coordinate, which is like a more global coordinate, extends over the fiber, the theta x is minus the argument of y minus c1. It depends on the position of y. It sort of rotates as you move the base point. So for that reason, we want to use this kind of a u-coordinate when you do the actual calculation. But modulo all those details, let's consider what are the Lagrangians we want here. We have two kind of Lagrangians now, because there's like a defect here. You can put a Lagrangian line on the left or Lagrangian line on the right. Let me call that, this is a T0, this is a T1. Over the fiber of these lines, I'm just going to still put a straight line Lagrangians. To be concrete, let's say we're putting in the u-coordinate. Okay. So now we can compute how does the harm of T0 goes to T1, how does the harm of T1 goes to T0, and how the composition goes. So harm from T0 to T1. According to our previous rule, you want to positively wrap T0. So you want to drag the boundary of T0 in a counterclockwise way. So it wraps into this way. It's a T0 wrapped. It will intersect T1 at one point in the base, but there are many points in the fiber. So this, roughly speaking, as a vector space, because this is not an algebra, it's not right to write like this, but just to show in the fiber it's just Z-many operators. Similarly, you can do the same calculation. T1, T0 is also like that. This time you wrap T1 and fix T0, and you will have some intersection point on top. We can represent these pictures also using these diagrammatic ways like we did for the New-Heck algebra. So for mapping from T0 to T1, so this is like, let's say, the composition time. I have my T0, I have my T1, and the map from T0 to T1 is like that, and you can put as many dots as you want. Each dot, say, I have 3 dots, that means I'm doing the Z cube intersection in the fiber. That means the fiber of T0 wrap around 3 times the intersect T1. We pick that intersection point in the fiber. And similarly here, you have T1 to T0. And now, how about the composition? The composition rule is very simple. You have this kind of bygone. You can straighten it, but at the cost of having 1 dot. So this represents a map from T0 to T1 and back to T0. We can actually draw the triangle in the base. So you have T1, and you have a T0, a copy of T0, and another copy of T0. So the first copy of T0 is positively wrapped. The second copy of T0 is negatively wrapped. So T0 map to T1, and T1 map to T0. and goes to this point. To compute the composition, you need to count some holomorphic disk, and that holomorphic disk in the base passes through the marked point, special point once. And the extra dot in the fiber represents the fact that when you use the u coordinate to represent the fiber, there are some factors that vanishes on the disk if you keep the x coordinate finite, and because some place on the disk y has to equal to c, so the u coordinate has to vanish. That causes the extra dot, extra wrapping. I can't explain that in detail here, but just saying the number of dots has something to do with how many times the disk passes through the marked points. All right. Yeah, the 3 dots represents I'm taking this intersection point in the fiber. So here is a, let me draw here. So say we have a T1. This is a T1, fiber of T1. And when T0 intersected in the base, in the fiber, this is a T0, the wrapped T0 in the fiber. So there are many intersection points. The zeros one, the first one, the second one, the third one. The 3 dots means I'm taking the third one, taking this intersection point in the fiber. Okay, so intersection point of the Lagrangian determined by a choice of the base intersection point and a choice for the corresponding fiber intersection point. Yeah. Suppose the input, you have no dot over this intersection point, no dot in this intersection point. That's like the input intersection point. Then in the output intersection point, there has to be 1 dot. All right. So I'm roughly on time here. So to summarize, what I've explained are some basic pieces of the calculation involved, how to compute harms between Lagrangians in this kind of a space. So the space, if you think, is always a disk with 2 stops and a bunch of punctures. You can isotope so that the puncture lies on the same line. So there are n punctures and defects. And you can put your Lagrangian, you can put, say, k Lagrangian, k strands of Lagrangians in this picture. And if I do not decorate the fiber with anything, I'm defaulting by saying I'm picking the straight line Lagrangian over each fiber. Yeah.
So you said every Lagrangian should be that as respect to this family structure.
Mm-hmm.
This is like the general setting for the requirement.
Right.
But you make this very precise. I roughly understand that.
Yeah. So here I'm taking a product symplectic structure on a total space. So I'm taking Lagrangian in each factor, so the product is a Lagrangian in the total space.
Yes, but I mean, so the Lagrangian is the product
It doesn't always come from this way. I'm describing some nice Lagrangian in this space. We haven't, yeah. So you can say consider arbitrary Lagrangian allowed by this Fukaya category. And you can, yeah, so that is a Fukaya category. We're considering a certain subcategory generated by these nice Lagrangians. We call those fibered Lagrangians. Conjecturally, yeah, conjecturally, those nice Lagrangians generate the Fukaya category, but we haven't been able to prove that yet. Great. But those nice Lagrangians, for all intents and the purpose, for the Lagrangians that we care, every Lagrangian can be expressed as chain complexes of these nice Lagrangians. So for our purpose, that's like enough. But it still is desirable to find a generation. All right. Okay. So if I give you the number of punctures and give you the number of strands in the Lagrangians, and you can consider this straight line Lagrangians, this kind of different choices of objects determined by how many strands you put on this bin or that bin. So this subcategory of this straight line Lagrangians, this is equivalent to the KRRW category. Okay, so I will explain what is KRRW yet. It is a category of a module over this algebra, KRRW algebra. What is KRRW algebra? It is a diagrammatic algebra of k strands, k moving strand with n fixed red strands. And the diagrams, you have this kind of a diagrams, like dots can be placed on the moving strands, and the moving strands can move as they wish. And the composition is by concatenation. So this is like the time direction. And they satisfy some basic rules. Some of the rules are like this. The crossing twice is 0, and one rule is like that. If you form a bigone between the black and the red, you have a dot, you straighten. And there's another rule which can be derived from these rules. Is that this guy minus that guy, this equals to, okay. So this category is pretty combinatorial and easy to describe. And our theorem from last year by Mina, Danilenko, Vivek, Yixuan, and me proves that this subcategory of category is equivalent to this KRW category. So that involves just the computing some endomorphism of Lagrangians. All right. But there are other interesting Lagrangians in the space that may not be of this straight line form. How do we represent those? And what are those Lagrangians? Let me just draw some examples. To recall that we have this Fukaya category of this yk and wnk is equivalent to this module. So this means like the subcategory generated by the so-called T-brains, where we call T-brain are of the form straight lines in the base, straight line in the fiber. So the functor going this way, is that for any Lagrangian here, I can associate to it a vector space from this this kind of a T-brain. So T is the direct sum of this T. I's are like the choices of placement. To consider all possible such T-brains, this nomorphism of the T is KRW. And if I give you some other Lagrangians in this space, if I can compute the Fukaya category harm from T to that L, I get a vector space that receives a right action of NT. So in that case, it's like a Unida embedding, mapping an L to that. So what other L's do we care about? Let me give you one example. So I'm going to draw this Lagrangian in the base, and in the fiber, I'm going to choose a different kind of a fiber Lagrangians. Instead of a straight line, I'm going to draw this kind of a U-shaped Lagrangian. I mean, it is coming from a small U shape around the stop, but after wrapping, both ends get stuck at the stop, you get this kind of a shape. So we call that a U fiber. This kind of Lagrangian is equivalent after some deformation to this kind of Lagrangian, where in the fiber, I get our familiar straight line fiber. So one of our group member, Eugene, shows that this kind of Lagrangian, the U shape in the base, the straight line in the fiber, after doing some gradient flow, can be deformed in the limit to this kind of a Lagrangian. That's one way to show that these two Lagrangians are representing the same object in a category. Or one can also do some floor theoretic calculation to show these two objects are the same by creating explicit maps from this guy to that guy and map from this guy to this guy and compose to get identity. The second approach is done by Elise and Vivek. You can also show that in the paper. This is done. Okay. So once we get this equivalence, you can break this U shape in the base by stretching it and stretch and break. So you can have this T1, and this is a T0, say shifted down by 1, shifted up by 1. You can say this Lagrangian is the same as this guy, direct sum of this guy. But that would be a lie because these two parts initially were connected by Lagrangian. The holomorphic disk can use this as a boundary. we want to remember that fact, so we want to put back a ripcord from this Lagrangian to this Lagrangian. So there is a correction, this delta from T1 to T0 of this form. This is the usual mechanism of a twisted complex where you correct a direct sum of objects by a degree 1, a differential, so that the delta square equals 0. There's nothing to check in this case. Delta square is 0. Okay, so that's like one interesting example where you can resolve some not obviously a chain complex of T-brane into a chain complex of T-brane. Another interesting example is this guy, where you just have the Lagrangian connecting the two special points, and you still put the U shape in the fiber. So for this Lagrangian, you may worry that this Lagrangian has an endpoint over the puncture. Similarly, you should worry about this Lagrangian has an endpoint in the puncture. You may worry the Lagrangian is not complete or it's not closed, it has a boundary. But let's remind you that these pictures are like in the U coordinate. In the actual X coordinate, in the geometric X coordinate, X would equal to U times U divided by 1 minus Ci. Sorry, my U and X were a little bit inconsistent with my initial notation. So you have this kind of a, this X coordinate are actually the physical coordinate. So if U were bounded and Y gets very close to Ci, so this whole factor gets close to infinity. So the actual shape of this Lagrangian, as you move over this point, is like this actual Lagrangian, the fiber get pushed up to infinity. So it's just to say it's a well-defined Lagrangian, has no boundary. Okay, so similar here, this is a well-defined Lagrangian, and there's a way to represent this guy as a T-brane complex. One can first rewrite this as a sum of this guy with that guy, and together with a differential from this piece to that piece. This is obtained by dragging this Lagrangian down to the bottom, dragging and break them into two parts. And now each part can be represented as a two-term T-brane complex. So in the end, you get this guy is the same as this guy, just being very quick. Okay, so it's a four-term T-brane complex. There's a different way. Initially, there's a different way to come up to this resolution by doing an actual Hamiltonian perturbation on the upstairs, and then stretching. I won't talk about that. So just an example where you have interesting Lagrangians resolvable by T-brane complex. Okay. So now let's relate this story to representation theory. So far I've talked about disk with 2 stops and some punctures. I'm going to specialize to 2 kind of cases. Where in the first case, I don't have any puncture in the middle, but I consider arbitrary number of k here. So I'm going to consider the direct sum of k from 0 to infinity. Let me introduce a notation here. The Fukaya category of the let me just use our old terminology. The Fuchsim K of this picture means I put k strands in this disk, and if I just do Fuchsim without the subscript, it means I want to consider all of them all at once. And this is the same as new hack K module, right module. If you want to connect this to decategorify this, we can take the K theory of this gadget. The K theory of this gadget is going to be equivalent to UQSL2 minus, which is sort of a boring. It's just going to be the polynomial ring of the lowering operator. So maybe to say the K theory, tensor with C, to avoid talking about the divided power. Okay, so this guy, you can say decategorifies to this the subalgebra of the lowering operator, half of the quantum group. How about the actual representation of a quantum group? Suppose you have a C2, the fundamental representation, acted by, say, UQSL2, hence acted by all the half of the UQSL2. This is realized by this kind of a picture, where you just have one mark point in the middle and one stop on the boundary. So I mentioned this is for you can still consider the Fuchsim of this guy, which a priori is k equal to 0 to infinity, Fuchsim k of this picture, where one stop translates into your WB is the sum of yi, not yi squared. And you will immediately complain that here we have this 2-dimensional vector space. Here, when k goes from 0 to infinity, you similarly have too many objects there. However, for k greater or equal than 2, this vanishes. So let's see the dictionary here. So for k equal to 0, you just have this guy. So this is C2 is highest weight vector, so V of a weight W1, and you have a FV of weight W1 minus alpha, or minus E1. This is the weight W1. So this is the corresponding to the vector V. And for k equal to 1, this category has this one object, corresponds to FV here. For k equal to 2, well, so you may wonder what happens to this guy. If you put a Lagrangian on this side, you can isotope this away, so it becomes like the 0 object. This is 0, so it doesn't contribute. And for k equal to 2, initially you'd thought I can stack 2 Lagrangians between the stop and the defect. However, this object is also 0. The way you can see this, you can either do a disk counting computation, that's, I guess, or you can do the KRW argument. So it's not easy, but not extremely hard to show that this is still a 0 object. So that's why you have a higher k bigger than or equal than 2, you don't have any contribution. This is the same as saying FFV equal to 0. Lower twice, you get 0. Yeah, exactly. So Mina mentioned the slight move being that this W1 defect and this E1, this T-brain line, they sort of shield each other. So together, this combination, how to say, is like nothing. You can take this away. So the remaining strands can slide away to infinity. That's one way to understand why this is happening.
If I remove the marked points, if I take Fukushima out of the disk with just one stop,
right.
Can I think of that as like a Verma module, or is that just some like?
That is like the trivial module. That's like the C, vector space C, with highest weight 0.
Right. So I can't make sense of anything that's corresponding to like just y0 minus something.
When you say removing, you mean replace that by just a plain no puncture, or replace it by a hole?
Just removing the hole.
If you replace it by a hole, then that is the Fermat module. I'm going to talk about that next. But before I talk about the Fermat hole, let me just finish talking about how does tensor product of C2 be represented by multiple punctures with one stop. This would correspond to C2 tensor C2. So you can say the highest weight of the first C2 called V1, second highest weight of the second V2 call it V2. So V1 tensor V2 is the highest weight of this guy. And suppose I'm acting from the right, say the right module. I've acting on this guy, distribute to be V1 F V2 plus V1 F tensor V2. Here, I wasn't being careful about the Q grading. There will be some like a Q factor appearing here. So the picture to have in mind is that each time you apply a lowering operator, you add a strand here, and adding a strand, you can deform it into this shape, which is the direct sum of this guy plus direct sum of plus this guy. However, you need to remember that when you stretch this, you are breaking a Lagrangian, so you need to correct that with a delta that goes from this end to this end. But if you just take K-theory of this object, you don't see the connecting homomorphism. It's just K-theory of this guy and K-theory of this guy, which this is like V1 FV2. This is FV1 V2. Okay, so Sujay is asking how to realize the Verma module. If you have an actual hole in your disk, then you can pile up as many Lagrangians as you want, and they never vanish. So the hole, together with some choice of like Q grading around the hole, realizes a generic Verma module of SL2. Verma of generic weight. So with the highest weight here, E corresponds to nothing on it. Actually, and say you have two V on it. So one can also compute endomorphism algebra of this Lagrangian, and that will not be the new HEC2 anymore, because when you wrap this Lagrangian, it will bend forward and intersect with itself in a different way, in more ways. So you have these extra kind of intersection points to worry about. So we did a calculation, and it matches with the thing people, Nas Vaz, who also computed endomorphism of the categorified Verma module. The algebra agrees with them. You mean for this guy? Yeah, right. Right, yeah. Right. Yeah, so for this with one stop, you do have realizing the module over the categorified quantum group, negative half of the quantum group. Okay, so here, when I implicitly saying that action on the given state, say action on a given state is by adding a Lagrangian near the stop, you may question me, what do I mean precisely by that adding a Lagrangian to the stop? And is there a reverse operation of a removing Lagrangian near the stop? The answer is yes. So in general, when you have two disks, so what do I mean by adding Lagrangian to a stop? Suppose you have some Lagrangian like this, and suppose you have some Lagrangian like that. You can put the two pictures together. So there's a functor, merge functor, that on the object level is just merge the two disks together. And the stop that's used in merging disappears, and you only still have one stop left. So this is how an element in the categorified quantum group can act on an element in a categorified representation. So on the object level, you don't learn anything new, but this actually is a functor. So it means the Hopf space between, you have another object in this category, you compute the Hopf here, that Hopf space maps to the Hopf space after merging. So merge on object level is just juxtaposition on the Hopf space level. This merge is never going to be fully faithful. And you may wonder, does this merging functor have an adjoint? Well, the answer is also yes. And the adjoint of merging, it has a left adjoint and right adjoint. And we use those adjoint to construct the raising operator. If like merging into these two strands means like lowering twice, you also have the adjoint. So I'm short of time, and just say it in word. Merge. Say some picture here. Say K1, K2. Say here has N1, N2. Has adjoints. And on the object level, you can see how it works. I'm just can do one example. Suppose you have this object in this category, this object in this category. After they merge, they become the two strands object in this category. And what is the adjoint? So let's consider the right adjoint first. The right adjoint can be done in this way. It's a sequence of operation. You first want to wrap positively wrap negatively, not positively. Wrap the Lagrangian negatively. So after wrapping negatively, they become of the form this way. And you can do a cut where they originally merge. You can do a cut and then split one Lagrangian to the left and one Lagrangian to the right. Now, when you split, there are two choices. Which one goes to the left? Which one goes to the right? You have two terms. Say this and that, or this and that. Drag some of them. Here, you may worry whether there are corrections between these two terms. There may be, but if you have this T-brain fiber, then there's no corrections. And then you cut. So then you can get a Lagrangian that's half ending on the stop and half ending on the stop. And then you want to correct this ending on the stop Lagrangian by positively perturbing it back to ending on the non-stopped region. So this will become this legal Lagrangian, and this will become this legal Lagrangian. All right. So the red adjoint would involve like you first wrap negatively, cut, and correct them, put them upright. You can think about the left adjoint would be like wrap positively and then cut and put them upright. So that's how you do it on object level. And there are also formulas for how the morphism would go if when you have some endomorphism of this guy, how it is split into endomorphism of the result. The morphism of the result is like sum of two terms, so we'll end up with a 2x2 matrix of morphisms. Okay, so this is just to show that the adjoint, you can say the adjoint abstractly exists. Here I'm just giving you a concrete recipe to compute the adjoints.
Does this recipe actually exist?
Yeah, this cutting procedure will needs to be carefully defined by counting possible disks that get lost when you do the restriction to this open subset. So you can either do that in a Fukaya category way, or you can use the KRW recipe because this red adjoint, this basically is induction, this is basically restriction to some subalgebra. So the adjoint would exist if you just use algebra. Yeah, and also Fukaya way of saying is useful because sometimes algebra doesn't extend. Yeah, so the short answer is yes, it does exist. All right. So these are like these adjoints of the merge operation. So next, I will use the merge operator to define a covering of a big space where, suppose I have a disk and I want to cut it in half. And suppose I have some, say, k equals to, say 10 strands in here, so this category. I want to be able to say this category is described by all possible ways of distributing K as K1 plus K2 on the two sides and use the merge operator to generate all possible objects in here. The obvious redundancy is that suppose you have some strands here, it can be generated multiple times from this constituent. So we need to correct for that redundancy, and that is this categorified bar complex will cancel out this redundancy. So in the end, you would say the Fuchsim sigma is Fuchsim sigma left tensor with Fuchsim sigma right, say sigma is cat. But this tensor is not the naive tensor. You can say it's a derived tensor over the algebra of Fuchsim, the thing in the middle, which is a disk with two stops, which is just our new hack category, new hack for summing over all K module. So this is a monoidal category, and these two are left and right monoidal module of this guy. So we're just doing some categorified tensor product. All right, I think I'll stop here, and thanks for your patience here. Yes.
So